Higher Maths, Unit 3, Practice Assessment, NAB 3, Outcome 4 on further trig relations, the wave function in this case. Now, there are 5 marks available here, and in order to pass it, you need to get 3 of those 5 marks. Now, this further technique completes the set of trig equations that you should be able to solve as far as the higher is concerned. The basic trig equation, that is, a simple trig equation, is an equation in the form of either sine, cos, or tan, I'll not bother mentioning that, of some form of the angle equal to some number. So that if I had sine 3x plus, put it into degrees, not put the degree sign in, sine 3x plus 10 equals 0.5, then the way that would be solved was simply by doing the inverse. 3x plus 10 is the inverse sine of 0.5, which of course is a set of answers for as many as you care to have, and then getting rid of the 10 and getting rid of the 3. So then that 3x would be, of course the first answer for that is 30 minus 10, and then dividing by that 3, that'll be the 20 divided by 3. Now that's the only type of equation you know how to solve, a simple trig equation. Any other concoction of sines and cosines and angles have to be reduced to simple trig equations in order to be solved. If you had combinations of one function, as long as it's of the same angle form, it makes a simple trig equation. If I had something like 3 sine 2x plus 4 sine, but it'd have to be also 2x equals something like 5. That's a simple trig equation. There's only one function form and one form of the angle. That would just connect up to 7 sine 2x equals 5, and then the same as before, divide by the 7, get rid of the sine, which produces of course a set of angles, and then divide by 2. That's a simple trig equation. However, if I had my 3 sine 2x, but then something different like a cosine, or even still a sine, but of a different angle form, of just cos x, I'll just put equal to 0 in this case, that's not a simple trig equation. I've got 2 different functions of, in this case, different angle forms. The only way you can solve that will be by somehow transforming that into a simple trig equation, or maybe a pair of simple trig equations. And the technique here is, you'd notice by this angle is double that angle, so you could make the angle forms the same by using the expansion for that. And the expansion for sine 2x is 2 sine x cos x, plus the cos x would equal 0. So that's 6 sine x cos x plus the cos x equals 0. Still doesn't look like a simple trig equation until you factorise out this cos x. Cos x times sine x plus 1 equals 0, and since they're equal to 0, that means either of the multiplying parts can equal 0, so you can split it into 2 simple trig equations. Cos x equals 0, or sine x equals negative a sixth. Simple trig equations. That's the second technique you have. It's called using the double angle formulae, but it only applies to the cases where one angle is double the other. Now this last part, this wave function, takes care of the case where you have different functions, so it's not a simple trig equation, but not of a double angle, that's the double angle type, but of the same angle. Now it doesn't matter what those angles look like, as long as it's the same angle form. It could be an x and x, a 2x, a 2x. And as long as those angle forms are the same, it's just these two that spoil you having a simple trig equation. And of course it doesn't matter what the coefficients are, it could be something like this. How would you solve that equation? This is the wave function. And the way that this is solved is because these two functions can actually be combined to produce a single function, a single wave, either a sine or a cosine. And it's called the wave function because it's like taking this sine, and of course a sine is a wave, and this cos, which is another wave, and it's like having the effect of 2 waves put together will produce one bigger wave. I'll illustrate that with a simple one. A simple one would just be, if I've got cos x plus sine x, I'll not bother putting the equation part of it because it's just this part I want to reduce to a single function so I can have a simple trig equation. What would that reduce to? I could show that graphically by drawing these 2 waves and adding them together? Well, sine x would look like this, going up to 1 and down to -1, and cos x would look like this. There's two waves going at the same time, and the effect of adding these waves together would just be by adding their corresponding heights, so that it would start off here at 1. They've both got the same height here, that'll be at 45 degrees, so this would go to double the height. Here we've got 0, it would be back to this point. Those two values, 0 and this added together, gives this. This would be double that, so it'll be down here. Back here again, I'm adding on 0, and finally I'm finishing off here. Could put in a couple of other ones. Round about here, halfway through, it should come to 0 because I've got the same distance above and below, and the same should happen over here. If I join those points together, I would have, not very well drawn, this wave, which of course would carry on the same as that afterwards, or carry on down below. I've got this wave again. In other words, it just makes one bigger wave. The wave function combines these two together. It's a case of what do I want to call it? Is it a cosine that's been shifted forward by this amount? Or is it a sine that's been shifted back by that amount? Well, you could go even further. Is it a cosine, well, it's difficult to show this one, that's been shifted back by a huge amount to here, but an amount still less than 360? Or is it a sine that's been shifted, again, a large amount forward to here? There's really four ways that could be written. It could be written as the cosine of x plus or minus some angle, or as the sine of x plus or minus some angle. And the choice is usually pick the one with the smallest shift to it. Well, in this case, because I've chosen this simple one, I know this point. I know when the cosine equals the sine. The cosine equals the sine at 45 degrees. And I know that the cosine and the sine of 45 degrees are both 1 upon root 2. So this height here, the overall amplitude, must be 2 times that. That's 2 over root 2. Now root 2 into 2 gives the other root 2. So this must have an amplitude of root 2 and a shift of 45 degrees one way or the other. Which means one form of this would be root 2 cos of the angle. Now if it's going forward 45 degrees, I would have minus 45. I'll put in the degrees. Or, just as good, would be root 2 sine of x, but it's gone back 45, so that would be plus 45 degrees. Either of them would do. Now that's the purpose of the wave function, to take this combination of waves, sines and cosines, and produce a single wave function from it. And of course, once you've got a single wave function, you can then, if it was part of an equation, transform this into a simple trig equation with one function of one angle form. But of course, you're not going to be doing it graphically by plotting them and measuring amplitudes and phases. You'll be doing it, in this case, algebraically. So as an example, I'll take this combination of sines and cosines, but notice it has to be of the same angle form, and transform it algebraically into some bigger single wave, so we'll just call that new amplitude k, of either sines or cosines. I think in this case I'll just put of a sine, of the angle. Now it could be plus or minus, depending on what kind of shift you want. I think in this case I'll just put plus a, and then the degree sign would go outside. This expression here can be expanded into two terms, just as this has got two terms. And then if the two parts are meant to be identical, because it's not actually an equation, this is an identity, that means all the parts must be identical. So the first thing would be expand this. Now it's just a case of what will I do with the k? Well, I know the k is going to appear in all the terms because it's multiplying this single part, but I think I'll just keep it outside just now. So expanding that would be sine x cos a plus cos x sine a. Now you may well pop the k's straight in. I think I'd rather do this because I want to make this expression look identical to this expression, which is some number of sine x, some number of cos x. So now we'll take the time to say, what have I got for the sine x? I've got k times cos. K cos A, and I'll put it inside these little cosmetic brackets just to make that stand out. That's the coefficient of sine x. When you have the form cos equals, you can end up with cos cos and sine sine, and then you won't get any confusion between identifying the corresponding coefficients. But I'll just take the time here because it makes it simpler. Plus k sine A, because remember A is a constant. K sine A of cos x, because x is the actual variable. Now we can equate the two parts. This is meant to be the same as that, so this number of sine x must be the same as that number of sine x. So that means that k cos A must equal 3. I'll put it down here. K cos A equals 3. There's a little equation with two unknowns. If you've got two unknowns, you'll need two equations. Well, here's the other one. What have I got for cos x? I've got k sine A. I think I'll put that in top for a reason that will become clear in a second. K sine A must equal, now that's plus k equaling negative 4, so that must equal negative 4. Now, as far as the marking for this question is concerned, the first mark is for making either this statement or the ones with the separate k's in it. I would say for making this statement because that's a much clearer form of it. And the second one is for making this statement here. And it needs to be both parts of this, where you equate the corresponding coefficients. So there's 2 marks out of the 5. Now the next 2 marks are just for finding k and a. And as far as the NAB is concerned, it just wants the 2 answers. It doesn't want any justification of the way you worked out the answer for k and the answer for a. It just wants these 2 parts. But I'm going to put down the justification here. The justification is this. I've got 2 equations in 2 variables. They need to be solved simultaneously. What's the technique I'm going to use to solve this pair of simultaneous equations? Well, there's various techniques like substitution, elimination, but there are other ones. What I'm going to do here when I've got trig terms is if you take equation 1 and you take equation 2 and square and add them, that will give you, I'll put it down, a k squared sine squared a, and adding on the second one, plus a k squared cos squared a, for the left hand side, is a negative 4 squared plus a 3 squared. Now there's a common factor of k squared here. K squared times sine squared a plus cos squared a would equal that side, and of course sine squared plus cos squared equals 1, which is why you usually jump straight in with just k squared equals those 2 numbers squared and added. So I'll just do that here. I like to put down this justification of where it actually comes from. If you square and add the equations, you'll have k squared equals negative 4 squared plus 3 squared. Or you may recognise that straight away as, in this case, a 3, 4, 5 triangle. K is 5. I'll just finish it off. So k squared is going to be 16 plus 9, which is 25, which means k is the square root of 25, so k is 5. Because the condition here is k is meant to be the amplitude, and the amplitude is stated as the positive amount. In the question it would say k is greater than 0, so that's why I've only taken the positive root here. So k is 5, gets you 1 mark. The way that you would find a is by taking equation 1 and dividing it by equation 2. That way you would have k sine a equals negative 4 divided by the other equation, k cos a over 3. And of course sine over cos turns into tan and the k's cancel out. So the next line will just read tan a equals negative 4 upon 3. You would just go straight in with, well, if you divide the equations, that means that tan a will be, and make sure you've got it in the order of the sine over the cosine, because that's where the tan comes from, is negative 4 upon 3. So naturally, a will be the inverse tan of negative 4 upon 3. Now this angle could be anywhere from 0 to 360. Now there are 2 answers to this. There are 2 answers because a sine wave, if you've got a sine wave and it's not in the correct position, then you can either think of it as having been shifted back by a certain amount, or having been shifted forward by the corresponding amount. And of course the two of these add up to 360. But this specifies which one it is. I want the one where it's been shifted back by the amount. So there'll only be one answer to this. The two answers that come out of this correspond to the two possible shifts, but this specifies which one you want. But you can get that just by checking these numbers here in your cast diagram, all sine, tan, cos. This says the sine is a negative amount, so the angles will be in one of those two quadrants. This says the cosine is a positive amount, which means the angle will end up in the fourth quadrant. So the angle you require will be this big reflex angle, where this angle here will be the acute one you get by solving the equation ignoring the sine. Remember, the cast diagram takes care of the sine for you. So just entering just the 4 over 3, not the negative part of that, gives you an answer of 53.1. 53.13, etc. for this acute angle, which means the angle you actually want will be the obtuse one, which will be 360 minus 53.1. So that will be 306.9. Notice I've not put the degree sign in because the degree sign is sitting outside of that bracket. Now that is the fourth mark. And the fifth mark is just for stating what you've already got, simply by writing that your 3 sine x minus 4 cos x is actually 5 times the sine of x, in this case plus 306.9 degrees. By making that statement, this statement here gives you the final fifth mark for doing nothing apart from putting the numbers back into that. Still, why complain? I deliberately in this one chose an example where this phase angle was a bigger angle. In all the variants of the NABs, they're all going to be acute angles. So try this question. So here's the question then. Notice that the nuisance of it is having these little degree signs in. It's always better in radians because you don't have to put anything like that in. Still, the first part would be, if I want to write it in this form, then expand this, expand the cosine of the sum of two angles. I'm going to do it in 2 steps. You can do that in 1 if you like. So that'll be k times cos x cos a minus, check your formulae, sine x sine a. Now, strictly speaking, each of these requires a little degree sign still, but nobody bothers to do that because it's such a cumbersome paste of a thing. And then tidy that up into, remember, x is the variable. I want to separate it so I can see the coefficient of the term involving the variable. So I've got k cos a times cos x. But then again, the thing about the cosine variant is you're never going to get them confused between the x and the a because they both say cos. So you know the coefficient of this cosy thing will be that 3. Minus k sine a, that's the coefficient because a is a constant, of sine x. That would be your first mark. Now the second mark would be, what are the coefficients? Well, the coefficient of the cos term must be a 3, so that k cos a must equal 3, and the coefficient of the sine term must be this 2. Notice it's a negative of this and a negative of that. That means that the k sine a just equals a positive 2. Now that's the second mark for equating the coefficients. I'm still going to set it out. How do we derive the results? If you square and add the equations, you'll end up with k squared is 2 squared plus 3 squared. That's 4 plus 9, which is 13. K equals root 13, and of course it's a positive value, it says that there. So I'm only taking the positive root. That's a mark. And if you take the equations and divide them, making sure you're dividing the sine by the cosine, that will give me, the k's will cancel, that will give me tan a equals 2/3. So a will be the inverse tan of 2/3. Now, inverse tan does have two angles, up to 360, but this specifies which of the two variants you want. Is it a shift back or a shift forward? Those are the two results. You're wanting this one, plus, that's actually the shift back one. You could sort that out by using the cast diagram, all sine, tan, cos, and the sine is positive, the cosine is positive, so there you are, the angle's in the first quadrant. It'll just be the acute angle you get from this. You get 33.69 and so on, but that is what you want. So the answer is 33.7. Notice, not degrees. The degree sign's already outside. That's the fourth mark. And then finally putting it all together, I'll write the whole statement out. Cos x minus 2 sine x is a bigger wave, amplitude root 13, of a single function. In this case we're calling it cos of x, and it will be plus 33.7 degrees. Putting those two numbers back in gives you the fifth mark, and there you are then.